Okay, for the next couple weeks, we're going to work on reviewing the major topics that we talked about in calculus this year. And starting with that, we're going to talk about limits, and we're going to work our way through derivatives, applications of derivatives, integrals, applications of integrals. I'm going to try to summarize everything we've done in a very concise manner. We're going to spend about 10 days on this. I'm going to give you a worksheet every now and again to do. But a lot of times you're not going to have homework except for to be working on either the current take-home test that you're doing or doing corrections on a take-home test or free response or something like that. So it's really on you to kind of be making sure that you're using this information to help you on these take-home tests and on your corrections that you're doing. So you should have a copy of these notes because there's a lot here, and I'm just going to kind of run through this and give you a brief little review here of what limits are. It says limits. A limit is the intended height of a function at a given value of x, whether or not the function actually reaches that height. Remember that it's not what is the y value, it's what is the graph getting closer and closer to as you're approaching it. And there's a few properties here. The one is the easiest one, the direct substitution. Are you going to have one like this on the AP test? Probably not. But if you could just substitute in the number, that is the limit. That is the height there. If it's a continuous function that is defined at that point, then number one here, define the limit as x approaches 0. I want to know what's happening as I get closer and closer to 0. Well, I can just plug 0 in there, and I can say, well, that's 2 times 0 minus 1, or that's negative 1. Right? On the AP test, it's not going to be that simple. They're going to throw some stuff at you, want you to know some tricks here. Right? There's certain techniques that show up a lot. One of them is factoring. I guess it would help if I put a limit on that one. This number 2 should say the limit as x approaches negative 2 of x squared minus x minus 6 over x plus 2. And the problem is when you plug in negative 2 that you get something that's undefined. These will always be on the no calculator part of the test because they're not going to let you have a calculator to look at the graph and see what's happening or look at the chart. They want you to know the algebraic techniques. And you just got to remind yourself, this isn't so bad to do. We could factor this. X plus 2 on the bottom. And on the top here, I could say what multiplies to give me 6, that subtracts to give me negative 1. That would be negative 3, positive 2. And then I could cancel out that x plus 2. And I could take the limit as x approaches negative 2 of what's left, which is just x minus 3. And the idea is that you can use some algebra to get to a point to use direct substitution. Because now I can just plug negative 2 in there, and I would get an answer of negative 5. But I can't do that in the original problem. Another one that shows up is number 3 here with the square root in it. Again, look at the limit. The limit is at negative 3. I can't plug negative 3 in there. I also can't factor this. This one is not very factorable, but this is one, I call it a conjugate use. Normally, we want to get the square root out of the bottom and move it to the top. Well, this is an example of one that we're going to move the square root to the bottom, and what's going to happen is it's going to allow us to simplify it. And again, how do you know how to do this? It's just practice. You see it a lot, and you're like, oh, I could do one of those things here. So what am I going to do? I'm going to multiply the top and the bottom by the conjugate of the top. Remember, conjugates is exactly what's there, but you change the middle sign. So the conjugate of the square root of 1 minus x minus 2 would be the square root of 1 minus x plus 2. And as long as I multiply the top and the bottom by that, I haven't actually changed the value of it. I'm going to erase some of this. On the top, you should remember what's going to happen with conjugates. The middle term should cancel out. But if I take the square root of 1 minus x times the square root of 1 minus x, do you agree that those square roots are going to cancel out, and I'm just going to get 1 minus x? I'm going to get the square root of 1 minus x squared. The middle terms are going to cancel out. One's going to be plus 2 times the square root of 1 minus x. One's going to be minus 2 times the square root of 1 minus x. And then if I multiply the end ones, negative 2 times 2 would be negative 4. On the bottom, do not multiply anything out, because the whole idea is we want this x plus 3 to cancel out at some point. Right? Just leave it like that. So on the top here, what do I have? I have negative x minus 3. Really close to being able to cancel something out. Could I throw a negative there on the top? And I'd get negative times x plus 3 on the top. I'm not going to rewrite all that. But then that would cancel. And I would have the limit as x approaches negative 3. On the top, I would just have negative 1 over the square root of 1 minus x plus 2. And so if you see a square root in the top, especially with addition, subtraction, and you don't see another way of getting that, this is a technique that shows up. Now I can do this direct substitution and get 1 minus negative 3, or the square root of 4 would be 2 plus 2. That would be a value of negative 1/4. All right, so those are some algebraic techniques. There's some on your worksheet that you're going to get today that are just substitution, and there's some that require a little bit of algebra there. So look for that. Sometimes you might have to get a common denominator. You really want to try some algebra skills on your homework today. We also talked about one-sided limits. Remember that that's just looking what happened as you're approaching either the left or the right. A lot of times this has to do with, we talk about asymptotes a lot. When does a limit exist? You have to prove that the left hand and the right hand limit are equal to each other. So whenever they ask you for something to prove that something's true or justify your answer, you're looking to show that the limit as x approaches c from the left of the function is equal to the limit as x approaches c from the right. Then the limit exists and it's equal to whatever you got to the limit there. This is also how you prove that a function is continuous. Also proves continuity. We've done a few examples of this in free response questions. If they ask you, is it continuous? You got to talk about limits, right? So remember that when you're dealing with free response stuff. So let's look at the next graph here. I kind of just drew this in, but just to kind of remind you about limits and one-side limits from a graph. Part A says, what is the limit as x is approaching negative 4 from the right, right? Positive means from the right. So if I find negative 4 over here, 1, 2, 3, 4, here's negative 4. I want to know what's happening as I'm getting closer and closer from the right. So it's like I'm coming in from this direction, and I want to know what's happening with that function. So find the graph as I get closer and closer to negative 4. I'm dealing with this little segment right here. And I want to know what y value is that approaching. It's not approaching a y value, right? It's just getting bigger and bigger and bigger. So we can actually give two answers here. I think the best answer here would be infinity, because it's just growing larger and larger and larger. You could also say no limit, because it's not really reaching a specific value. And we'll talk about that at the bottom in a minute, about one-sided limits and giving answers of infinity. So infinity or no limit exists would both be acceptable. Find the limit as x approaches 4. 1, 2, 3, 1, 2, 3, 4. That would be right here, right? So go up and find where that is on your graph. That would be right here. So the limit is just what the y value is there, right? That's just a continuous function. Nothing tricky there. The limit would just be that y value, which is 3. If I asked you to find the limit as x approaches 3, we'd have a problem there because those don't meet up, right? If I asked you as x approaches 3, this part's up here, this part's down here, the left and right hand limit are not the same. So that would be an example that there is no limit. Oh, I think that might be the answer on the next one here, huh? Sorry, I jumped the gun here. Find the limit as x approaches negative 3. Negative 3 is right here, and we got a problem. Coming from the left, we're up here on this segment of the graph. Coming from the right, we're down here on this segment. Those do not meet up, so we have to say that no limit exists. For some reason, people forget a lot about limits, but they're not that terrible to do. It's just remembering the rules here. So I kind of summarized this for you about when to give an answer of infinity or negative infinity. It's really the same as saying there is no limit, but when you're giving a one-sided limit, you're kind of saying what's happening. Unlike part C, we can't say infinity there. Like, there is just no limit there. But if you give a one-sided limit, and you can say infinity or negative infinity. On the AP test, if it's a free response question, they would accept either one. They would accept infinity or negative infinity if it was negative infinity, or does not exist. Multiple choice, they would never give you both of those options on the same one, so don't worry about getting confused about that. Okay, the other big thing I want to touch on with you is how limits relate to asymptotes, and it seems like that's showing up more and more on the AP test every year. So I kind of threw a lot of stuff in here, but limits and infinity. Forget the limit part at the top for a minute and just read what my sentence there says. It says, if a function has a vertical asymptote at x equals c, then the limit as x approaches c will always be infinity or negative infinity. So if you take the limit and you get an answer of infinity or negative infinity, that means there's an asymptote. If you know there's an asymptote, that means that the limit's going to go to infinity or negative infinity. The other big thing is if you take the limit going to infinity. So if you get an answer of infinity or negative infinity, it's a vertical asymptote. The other part of asymptotes are the horizontal asymptotes. And that's if you take the limit as x is going to infinity, that's this top part here. If you're looking what's happening as x is getting bigger and bigger and bigger, or as x is getting smaller and smaller and smaller, if you get a real number, then that's the horizontal asymptote. And so this is kind of just some little algebra for you here. If you have any real number over x to any power, and x is just getting bigger and bigger and bigger, what is that always going to equal? If I plugged in like 10 and 100 and 1,000, what's that always going to go to? It's going to go to 0, right? And this would actually be your horizontal asymptote. So both horizontal asymptotes and vertical asymptotes go hand in hand with limits. It's just remembering which rules go with which. Number 5 here says, at what values of x does no limit exist? That's another way of saying where would the limit be infinity or negative infinity, because remember those mean the same thing. Which means we want to kind of think about where would the vertical asymptotes be. So that's kind of asking us, where are the vertical asymptotes? So be really careful on this. You got to kind of factor On the bottom, we can factor this into x minus 5 and x plus 5. But on the top, what can I factor that into? That multiplies to give me 10 would be 5 and 2, and adds to give me 7. So this one's kind of tricky here because you might say both 5 and negative 5 have no limit for them. But because I can cancel out this x plus 5, that just means there's a hole there. It doesn't mean that there's an asymptote. So the answer here would be at x equals 5, there would be no limit because that means there's a vertical asymptote in that. And this was in this little review book that I had. It said if you're ever trying to simplify a problem and you get down to a number divided by 0, that also indicates that there's an asymptote at x equals c. I don't feel like we do that very often, but if you ever see that, that's something to think about. Horizontal asymptotes. Let's talk about those really quickly. Horizontal asymptotes are when you take a limit that is going to either plus or minus infinity. So if you see a limit going to plus or minus infinity, that's the same thing as asking you to find a horizontal asymptote. There's a few ways we can do this. If this is a rational function, remember that we can always do the little rules. If the degree of the numerator is less than the degree of the denominator, then it will always be y equals 0. If the degree of the numerator is equal to the degree of the denominator, remember that it's the leading coefficient, and that's what this means. And we'll look at an example of that in a minute. And if the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. It's just going to keep getting bigger or smaller. Those are rules that you've learned since Algebra 2, but they're really easy to forget. Even if it is a rational function, this bottom part always works. If you feel like you're never going to remember those rules on the day of the test, remember this rule. To find horizontal asymptotes, all you have to do is divide everything by the highest degree of the denominator, and then take the limit going to infinity. Because if you do that, remember that anything over x is going to go to 0, and so we're going to be able to work that out. So we're going to do a couple of these so I can remind you how to do this. And these are kind of just nice handwritten ones here. The limit as x approaches infinity of 4x squared. Well, first of all, if you're thinking about in terms of numerator and denominator, right now this one's over 1, which means think about what's going to happen. If I just keep plugging in bigger and bigger numbers for x in that, what's going to happen to my function? I don't need a calculator to even do that. If I plug 10 in there, what's going to happen? I'm going to get a nice big number. What if I plug 100 in there? I'm going to get an even bigger number. If I plug 1,000 in there, I'm going to get an even bigger number. Because there's nothing in the denominator, there's no x in the denominator, this is never going to get to a specific value, which means it's just going to keep going forever. It's going to keep going to infinity, or you could say there is no limit, which also means there is no horizontal asymptote. For the second one here, you have those rules right on the previous page, and so you could look at that, and the degree of the numerator is smaller than the denominator. So looking at that, it means this should go to 0. But if you forgot that on the test, if you see a limit going to infinity, or you see something about horizontal asymptotes, you can just divide everything by that biggest degree of the denominator, which happens to be x to the third in this one. And so watch what happens. I would get 4x squared divided by x to the third minus 3x divided by x to the third over 2x cubed divided by x to the third plus 4x squared divided by x to the third minus 7 divided by x to the third. And I'm going to go through and simplify this, and the more you do it, the more you'll not spend so much time on it. But if you agree this with the x squared over x cubed would be 4 over x minus 3 over x squared all over 2 plus 4 over x minus 7 over x cubed. Now this is where this comes in handy. If you are looking at the limit as x goes to infinity, that's where my little thing came from earlier. If you have any number, if you have any number over x to any integer, any number really, doesn't have to be, if you keep plugging in bigger and bigger numbers for x, you're going to keep getting a smaller and smaller number closer to 0, right? This is always going to equal 0. So this is why this shortcut works, and it's actually why the rules we have work, because this is going to go to 0, this is going to go to 0, this is going to go to 0, and this is going to go to 0, and I'm going to be left with 0 over 2, which is just 0. That means that the limit as x approaches infinity for that problem is equal to 0, which also means that you have a horizontal asymptote at y equals 0. That's why if the numerator and the denominator are the same degree, you can just take the leading coefficients, because everything else is going to go to 0. If the denominator is bigger than the numerator, then the top's going to go to 0, and so you'll get 0. Right, that's why those rules are there, but this is something that comes in handy. So you're welcome to use just the rules, or you're welcome to use this, but it is something of how we can do limits. All right, so this last thing here is just me summarizing everything we did with limits, all right? This is the least you need to know about limits. The limit of a function at a given x value is the height of the function that it intends to reach. Not the actual value itself, right? Sometimes it's not what's actually defined. Remember that a function can have a limit even if it's not defined at that point. It can be undefined at that hole, but it's still getting closer and closer to it as long as the left and the right hand are meeting each other. That leads to the third one here. Really, really important. If the left and right hand limits exist and are equal to each other, then that's how you prove that a limit exists. It's also how you prove that a function is continuous. Remember that a limit will not exist if they don't meet up, but there's also, it doesn't exist if it keeps going forever. So if for infinite growth, or it oscillates, like kind of goes back and forth, back and forth. Most limits can be evaluated by substitution, factoring, or using conjugates. And then remember, worst case scenario, without a calculator, this isn't very feasible. But if all else fails, remember that you can kind of make a chart, pick values close to it, and see what's happening. If you're allowed to use a calculator, then you can always definitely look at that. And remember the big connection between vertical and horizontal asymptotes. What I have for you today is a worksheet, and this worksheet actually has some examples in it. So my advice to you is to kind of look at those examples as you're doing the problem, especially the compound fraction problem. There's a couple problems on your homework that involve fractions, and I didn't do an example like that, but there's an example on the first page of that worksheet. It seems like a lot, but they're just really spread out. I think there's not that many problems. But work on them, and this is due tomorrow for homework, okay? So we'll go over some questions, and then you will turn it in. So make sure you get it done.